at Princeton, where she also reads the PLI Institute, which is the Princeton Language Institute. She has done some seminal work in understanding language models and has been on the papers that were foundational language models that are now so prevalent in practice. So no better person to learn from on how to train large language models. So take it away, Danqi.
Thank you so much for the introduction. Is the mic working?
Yeah.
Okay, good. Yeah, thank you so much for coming. So I was asked to give a tutorial about how to train large language models. So before I get started, I would like to set an expectation of this tutorial and tell you a bit about where I come from. So my background is natural language processing. So I do a lot of empirical research. I say this because I know there are a lot of theorists sitting in the audience. And over the last few years, just like many of us, so our focus has been shifting to trying to understand and also train large language models. So we do a lot of experiments at Princeton. Most of the experiments on the fine-tuning stage, continue pre-training. We also do some small-scale pre-training experiments. I say this, I also want to emphasize that I come from an academic background. So most of our research focuses on academic context. So a lot of things we have been seeing over the years is really what are the research questions in this training pipeline of large language models we can actually help answer. When I set out to actually give this tutorial and to tell you what are the best things or what are the most important things you should know about how to train large language models, train the strongest large language models, I just realized that there are a lot of things I actually really don't know because a lot of the cutting edge state-of-the-art large language models really come from the industry. So a lot of the content in this tutorial will be drawn from the basic public knowledge and also our experiences in these academic research projects. So if you really read a lot of the papers from the industry technical report, you still find there are actually a lot of details that actually still remain pretty opaque. And we actually need to conduct it still requires a lot of rigorous experiments to verify these findings. And still many findings today are still remain as practices, and they definitely need a lot of the scientific understanding to really help us figure out what is actually really important for building large language models. So this semester, actually this week is the first week at Princeton. So we started a new course, a graduate seminar on large language models. So I'm actually really work hard to figure out what should be the actual reading list for the students to learn about what are the best practices of training large language models. Actually, I actually figured out this probably is still the kind of list of papers that we should let students read. These are all the technical reports of the current large language models, including Llama 3.1, Gemma 2, and many others. So this technical report do not include, say, all models from OpenAI or Anthropic. But still, we have quite a set of papers about the current strongest large language models. And I don't know how many of you actually even spend time reading these papers. If you open these papers, these papers are just very different from the research papers that we are used to reading, because there are just a lot of things that actually not so clear to us. You're trying to understand what are really the exact things that go into that training pipeline, but still there are a lot of things you just cannot figure out. So how should we learn from this? So I still encourage you to try to read through these technical reports of the current large language models. But there's still many other scientific research papers. I would say most of the papers from my research group fall into this category. So they conducted at a smaller scale, probably more rigorous and more controlled. But still, we have to admit that there is a clear gap from the experiments that we have been doing, and also what are actually really the cutting edge, modern large language models, the state of the art. So throughout this tutorial, I will try to cover something I learned from these technical reports of the current models. But I also cite a lot of the more scientific research papers along the way that I think you probably should know. Okay, so I will do my best to tell you some of the things I find actually exciting, and some of the trends probably actually some of the trends are pretty emerging trends that we should actually know about. I also tell you some of the work that have been done in my group. So this tutorial will be on the training pipeline of the current large language models. So naturally, I will divide this into two parts. One part is about pre-training. And another part is about post-training. So I've used a quote here from the Llama 3 paper report. So pre-training, simply basically like we take a model. We take a massive scale of the unlabeled text from the internet, and we basically do next word prediction. I think everyone knows about this. And the post-training, you can basically think about is basically everything we should do beyond the pre-training. So according to this definition in the Llama 3 paper, so in post-training, the model is basically trained to follow instructions aligned with human preferences and also try improve some specific capabilities, including coding and reasoning. Okay, so I'm going to divide my tutorial into these two parts. Actually, this morning, this morning I actually decided to switch the order of the two parts. I'm going to start with the post-training, and then I will come back to talk about pre-training. Because I really think that probably post-training is actually probably more relevant to many of us in this audience. There will be actually many natural questions we can ask in the post-training stage. But I'll also go back to the pre-training part and tell you what I think are some really interesting questions to ask about. And to make really, the last thing I want to, before I dive in, the last thing I want to emphasize here is to build really strong large language models. It really involves different component, different aspects, including data, algorithms, and model architectures. So I'm not going to talk about anything about model architectures today. I knew there was a tutorial on transformers yesterday. So in this tutorial, I'll talk about data and algorithms. But I also want to emphasize that probably many of you also know that I actually also think data is probably currently the most important aspect, the deciding factor of the performance of the current models. So I will probably mix these two parts together, but I just want to emphasize that I will spend a lot of time just talking about what is actually the data that people use for training models, and what are the kind of consideration we need to think about in data curation and data selection. Okay. Okay, as I said, I switched the orders. So I'm going to first talk about, so I still put part 2 here. I will start with talking about what is actually post-training. And if I have any questions, feel free to interrupt me, and I'm happy to take questions anytime. Okay, so when people talk about post-training, usually we think about there are basically 2 stages. This is actually a simplified view. I will tell you later, people right now really have many different ways to think about the different stages in post-training. But the two, this simplified view, the 2 stages of post-training include supervised fine-tuning or SFT, and the second stage is called preference learning. For the supervised fine-tuning, there is also another term called instruction fine-tuning. So the data that has been used in this stage, supervised fine-tuning, basically has this format of prompt and the response. And the learning objective is actually very standard. It's basically just next token prediction. You take the prompt, you take the response, and then you are going to basically predict every single word in the response. So these 2 stages actually first come from the Instruct GPT paper in 2022. So I took the figure from that paper. So for example, the prompt here is explain the moon landing to a 6-year-old. And they ask human labelers to actually write down the response to this prompt. And after we collect a large set of this kind of supervised fine-tuning data, you can basically fine-tune the language model on such data. That's basically the first stage called supervised fine-tuning. So I would just stick to this term supervised fine-tuning because I realize these days people also sometimes use instruction fine-tuning to also include a second stage of preference learning. So to just try to differentiate these 2 stages, the first stage I'll call it supervised fine-tuning. Okay, the second stage is preference learning. And there is actually another very popular term here, the RLHF, the reinforced learning from human preferences. But basically, the idea is that if you have kind of preference data in the form of this prompt, input prompt, and one winning response or called preferred response, and one losing response or one dispreferred response, and you need an algorithm this algorithm could be either like a reinforcement learning, like a PPO, or it could be some offline or preference optimization methods, like a DPO, to learn from such data. So I said like this term reinforcement learning from human preferences is actually a very popular term. But today I was just use this word, this term preference learning, because these days there has been just a lot of debate about whether we actually need reinforcement learning to learn from the human preferences. Actually, if we actually take a closer look at the preference learning data, actually a lot of preference learning data actually even doesn't come from the humans. They come from like a large language models. So both the preference, reinforcement and the human preference are actually not a really very rigorous terms today. So I also take this figure from the Instruct GPT paper. So basically, the format of this kind of data is you have a prompt like explain the moon landing to a 6-year-old, and then you have like a bunch of responses in this, like 4 responses. So all generated by models, and they ask human labelers to actually rank for example, in this context, like in this example, 4 responses. Like say the D is actually better than C is better than A, and A is equal similar to B. And you can basically simplify this and convert this into the pairwise form, like in the form of the prompt, winning response and losing response. Okay, so this is basically like the kind of like a simple view of the 2 stages. So now let's try to dive in and try to look at like what people have been doing in these 2 different stages. So let's start with the easy one, the supervised fine-tuning. Again, in this format of the prompt and the response. Since there isn't much thing I can talk about actually learning, because people just do very standard next token prediction. So the research questions people, or actually some practice that people have been actually thinking about is, how should we actually even get these prompts? How should we get the responses? There has been also some like a variation here that whether the responses include a chain of thought and reasoning or not, or is just like a simple answer to this prompt or not. And actually also a very important question to think about is, if we have collected a lot of the prompt and the response pairs, how should we actually combine and select these data sets for instruction tuning? So these are some like practical questions and research questions we should think about. Okay, so next I'm going to like walk through some of the ways that people have been actually using to collect the supervised fine-tuning data sets and some considerations here. So basically, I think there are actually like kind of like 4 types of the supervised fine-tuning data sets. The first type is basically people take existing supervised data sets, for example, NLP data sets, and try to repurpose these data sets into the supervised instruction tuning data sets. So some notable examples include supernatural instructions and the FLAN series, like FLAN V1 and FLAN V2. And when people try to convert these existing data sets into this kind of instruction tuning format, so there are also some like options about whether you should actually write down some add some human written instructions or chain of thought reasoning. And the second type of this kind of supervised fine-tuning data set is basically like for both the prompt and the response should be all like basically crowdsourced and written by humans. So basically human written from scratch. Some notable examples here include like Dolly from the Databricks, and also the Open Assistant data set is actually a very popular and a very useful data set for building the chatbots today. So these are all like crowdsourced. Both the prompt and the responses are written by humans. And there are also a lot of other instruction tuning data sets out there that the responses not necessarily just written by humans. They can actually be generated by the large language models like ChatGPT. For example, like ShareGPT is one of the examples. So basically, there's the one platform there. So you can basically write down your prompts in this platform, and so basically the prompts are from the humans, and the responses are generated by models. And there is also another very important data set called ArcherChat. It's basically also collecting this format. And finally, I also want to mention there are also some other instruction tuning data sets. The instructions can be also just generated by large language models. So there's one important paper called self-instruct. Basically, you just give the large neural models some seed instructions, and then you just ask model to spell out and generate more instructions by the large neural models, the prompts, and the responses also generated by models. What I want to emphasize here is there are actually many different variety of the instruction tuning data sets. If you just count like all the resources we have, like even the open source resources out there are actually many instruction tuning data sets out there. The question is, if we really want to build a very strong chat model, how should we actually consider using those data sets for building models? And I'll just tell you like one example. This is actually pretty is like a more relatively recent effort. So this model is called Tulu V2 from Allen Institute. So Tulu V2 essentially is one collection of the instruction tuning data sets. So if you just look at all the instruction tuning data sets actually listed here, it actually includes a lot of the data set I already mentioned, like FLAN data set, chain of thought, open assistant, shared GPT. And there are also a lot of the data sets just generated by ChatGPT and the GPT-4 models. And there are also some data sets have been actually like handwritten by humans. So it's basically like quite a variety. And for each of these subset of this instruction tuning data sets, they also have a very different number of examples. So the question, the research question we should ask is, how should we even decide the data mixture of all this instruction tuning data? And how should we even decide which data is more important, how to use them? So just give you one example here. So people did a lot of trials and errors here. So Tulu has one version like called Tulu V1. So if you just consider the basically two different data mixtures, you can get very different results. Like this basically average across many different downstream tasks. So the research question we should ask here is, what should be the notion of the high quality data in instruction tuning? And how should we decide the data mixture of all these instruction tuning data sets and which examples we should use? I don't think we really have an answer here. I just want to tell you what people have been doing these days. These are still like a relatively new efforts. So next, I will just very quickly talk about one work that came out from my group this year. So this work was led by two PhD students at Princeton, Monjo and Sadika, and it was published in ICML this year. So I'll just give you one idea or one possible approach of like how to select the instruction tuning data sets. So there are actually many other ways to do that. So in this work, we basically propose to use this kind of influence formulation to decide how to use the how to pick the individual examples in the large collection of the instruction tuning data sets to decide like what basically this is actually really like a very classical machine learning concept. Basically, we will try to define like estimate what should be the influence if we actually do like one gradient descent step on this training example. What should be influence of this particular example on a set of target examples we pick? So basically, I'm not really going through all these kind of formulations. Basically, like the influence estimate is like a really a classical concept, but we actually made a lot of efforts to make this work. To make things work for the, like Adna optimizer and also for instruction tuning examples. So instruction tuning examples, the one specific character about this data set is they have very different tokens. If you can't think about the loss, it should be actually the average loss of the different tokens. So that is actually like kind of one challenge of selecting instruction tuning data sets. And another really key point of using this kind of influence formulation for data selection is actually we have to make this work for like a very large models. So really how to make things work, efficiently is really the key here. So I just give you like a quick idea here. Here, basically we did a lot of approximation here. We first used the LoRa training instead of the like full gradient training. And we have to do some kind of random projection and then try to store the gradient features of all the examples in the instruction tuning data sets. And then we pick a set of the target examples. and then use basically the cosine similarity between this cosine feature, between the gradient features that we stored in the data store, and also the target examples to decide which examples could be actually more useful for basically instruction tuning for the target tasks. Okay, go ahead. Yeah. So, sorry. So basically the idea, I should actually put more details here. It's basically like if we decide, try to estimate the influence of one training example on like one particular validation example. So we try to basically take one gradient descent step and to see how the loss would actually impact on like particular target example. But we have to make this for Adam basically. Yeah.
So it's roughly which gradients.
Yeah. Yes, exactly. Yeah. Okay, so I'll just show you some results here. So we actually did a bunch of experiments in the paper. So something we actually find very interesting for like such data selection approach is, so here we basically use the Llama 2 7 billion model to select examples. So the red bar here is that if we just use all the instruction tuning example here, so we get basically an average performance of 53%. And if we just do like a random selection of 5% of examples, the performance would drop. But if we use this kind of influence formulation to select examples, to select just 5% examples, we actually find that this could work actually better than using all the instruction tuning examples. That really means that we actually have other settings in the paper. That really means that there is actually really a room for like selecting instruction tuning examples for improving the general performance of such models. So I want to emphasize one particular setting here. I put it called less T. So this is actually one transfer setting. So here, basically the instruction tuning examples are selected based on one like a Llama 2 7 billion model. But we use the example that's selected from the Llama 2 7 billion model to instruct fine-tune, like either Mistral 7 billion model and the Llama 2 13 billion model. We find that basically the gradient features can be, the example that's selected based on these gradient features can be actually transferred between different models. So that really means that using this kind of model-aware approach actually it could be a viable approach for selecting instruction tuning examples for probably even bigger models. But we only did experiments for Llama 2 7 billion and the Llama and the 13 billion and Mistral models. Any questions about this part?
Yeah, my question was about the default. So I don't think I quite understood the transfer setting. So the gradient is being taken with respect to which.
So the gradient is basically for all the data selection part is based on the Llama 2 7 billion. And after we select the examples, we basically train the Llama 2 13 billion or the Mistral 7 billion on the select examples, and then we evaluate the performance on basically the target model.
I see. So for the plot there for the T, that is for Llama 2 13 billion, but it could also be it's also somehow uses Mistral 7B.
Oh, sorry. Okay, sorry. Yeah. So all the results here are like a different subset of instruction tuning examples that we train Llama 2 13 billion on. So this is on the full data set. So the random 5%. These are the 5% data that are selected by the Llama 2 7 billion. These are the 5% selected by Llama 2 13 billion model. And all the results here are actually evaluated on Llama 2 13 billion models.
Is the performance of the Llama 2 model in some way upper bounded by the model you used to select that 5% data?
Not necessarily. Honestly, I cannot really explain why this actually even outperform this. So in the Mistral settings, the two bars are actually pretty similar. But at least this shows this kind of transfer setting actually works to some extent. Yeah, I cannot really explain why there is actually even some improvement over there. Yeah.
Is there any analysis in the papers that what kind of the 5% of, like which type of data tends to transfer between more and then tends to have bad performance?
Yeah, it's actually very interesting. Like we actually have some examples in the paper. We also compare to a lot of other like more retrieval baselines. We find that if you use those retrieval baselines, you can always find some like some similar examples that share some surface forms. But we actually, for the examples that we select here, we find that the instruction tuning examples usually share some kind of underlying like task structure or some reasoning structures that actually you cannot just tell from the surface form of the instruction data. So that's actually why I think the gradient actually features play a big role here. Yeah. Okay, so I actually don't just want to give you a kind of brief introduction about this part. I want to tell you like what kind of things people have been thinking about selecting instruction tuning example. This is one example, and there could be many other ways for selecting instruction tuning data.
Have you tried to find if the influence indicator you are using are correlated to other more simple indicators like the difficulty?
What do you mean by the other metrics of difficulty?
For example, you have another indicator could be the difficulty of the prompts or questions, and if someone can imagine that the more difficult question benefits the model more, and you have this can be difficulty can be calculated more easier because you just need to see if the model output is aligned with the training data to see the loss. So have you seen if your indicator really better than these more simple ones?
I'm not so sure like we did such analysis. Yeah, let's move this question offline. Yeah.
How many iterations do you think for, even though it's like 5%?
For the gradient training, getting the gradient features, it's actually okay. That's a good question. So to make the whole thing actually very efficient, we actually only select like a very small subset of the data for estimating the gradient features. I think we did 4 epochs, and we actually aggregate over the 4 epochs to calculate the gradient features.
Okay, but you don't overtrain on the 5% that you substitute, or do you just I guess my question is like 5% of the data, does it also translate to 5% of the?
Also, the gradient features are pre-computed. It has nothing to do with this 5%. So we calculate the gradient features for all the instruction tuning examples. And now we decide how to select the examples based on some target examples. And at this point, we decide to take the 5%. So we not just train on the 5%. We estimate the gradient features for all the examples.
I think the question maybe you are trying to ask is after you select the 5%, how long do you train that for? Is it trained for the same time as the 100%?
Oh, I see.
Or like you need less training with the good examples?
That's a good question. Honestly, I cannot really remember. We just train until it converge, basically. Yeah.
So it could happen that they require the same amount of training even if the data.
Yeah, I agree. Yeah. Okay, so let me move on. So instruction tuning is still relatively simple. It's basically the prompt and the response form. So next, let's move on to this like the second stage of post-training preference learning. So essentially, we need to learn from this prompt and the winning response and the losing response. This kind of like the pairwise response data. So similar to the instruction tuning, so there are also a lot of the kind of practical and research questions we need to think about. So first question is same, like how should we collect such prompts, right, for preference learning data? And how should we get the winning and the losing responses? And actually very important thing to think about is who or what should actually use to be decide which is actually the winning and which is the losing response. These are all the kind of practical questions we need to think about when what actually goes into the preference data. And on the learning side, on the algorithm side, so right now there has been a big debate between like the online preference learning methods and the offline preference optimization methods, such as PPO versus DPO. So just to give you like kind of a sense of how the data and also the algorithms actually interact. So, and also my view of what things actually really happen in this space. So my plan is to next, to first to tell you like, discuss what are actually the algorithms that have been used to learn from this preference data. And I will tell you some work that we have done in this space. And I will present some empirical findings we learned from the experiments. And then finally, I will come back to discuss the importance of data. Hopefully, this will actually make a bit like a more comprehensive, like a more full picture of what things are going on here. Okay, so I will start from like the RL side. So I will first talk about what basically like what is RLHF, what is reinforced learning from human feedback. So the setting here is assume that we have our preference data. Again, the preference data based in this format of X, Y, W, the winning response, and the YL, the losing response. I hope that most people actually already know this, so I will go a bit faster here. So basically, the first step here is you need to train a reward model to using this preference data. And the default way of doing this is to use like something called a Bradley-Terry ranking objective. So basically, for here you have a like term reward model that actually parameterized by this like theta. So the R theta X Y basically measures how good this response Y is following the prompt X. So this R theta basically assigns a scalar rating given like a pair of the X and the Y. And after you have collect this kind of preference, pairwise preference data, so basically you learn, use the maximum likelihood to learn from this objective from such data. So it's just basically like such an objective. And in the first like instruct GPT paper, they collect 4 responses, and then you collect this kind of ranking between the 4 responses. But you can easily convert this kind of ranked list into like basically like the K-choose-2 pairs of the pairwise preference data. And then you just sum up all of this loss and divide it by the basically the number of the pairs in such a ranked list. I just want to make sure that everyone knows this before, right? Okay, so the second step is to start from the supervised fine-tuning model that actually comes from the previous stage. And start with this SFT model as a policy model. And you collect a separate set of prompts. And you take a prompt sample from like a separate set of prompts. And you start from this policy model. And then you sample a response from the policy model at every single iteration. And then you check the reward model. And the reward model will give you basically a reward of how well this kind of response Y, sample response Y, actually follows this prompt X. And then you basically use this reward to go back to update this policy model. That's basically how like the RLHF works. And additionally, they also add a like per token KL penalty to make sure that the policy model will not deviate too much from the SFT model. Go ahead.
You mentioned earlier that like for multiple sort of responses, they're usually ranked. How does this transfer to like the R data like that's been given here?
Okay, so the question is if there are like multiple responses of like 4 responses, how to convert this into pair?
Like what I've traditionally heard is that usually they get ranked or something like that, and then that gets input into like a reward model. And I was just curious how that sort of translates to our data that you say measures how good a response is given like a prompt.
So if you have a ranked list, let's say you have 4 responses, you can basically like take any pair from this ranked list. So D is the winning response, C is the losing response, D is the winning response, A is the losing response. So basically you can convert this into like K chooses 2 pairs of the response data.
Oh, I see. And like this, like for example, if you ranked it like 1 to 4, is our data just 1?
You can just convert this into 6 pairs. Yeah, I should say like actually a lot of preference data actually direct collected from this kind of pairwise form. It doesn't have to be this ranked list form. But if you have the ranked list, you can easily convert the ranked list into the pairwise form. Yeah. Okay.
I guess probably the question was like, to do with R theta. I think you learn R theta to predict which one would win. So R theta is what you learn.
Yeah, that's true.
Okay, so this basically how like the this kind of Iterative approach work for like learning from the preferences. So this thing definitely works very well, but it also has a lot of like drawbacks or shortcomings that people have been actually criticizing. For example, for this pipeline, it really involves multiple models. So it involves a supervised fine-tuning model, involves a reward model, and it also involves a policy model. And it also requires like multiple stages of training. You have to first train the reward model on the preference data. And then the next stage, you are going to optimize the policy model according to the reward model. Then it's actually a really complex pipeline, and it's actually hard to get it right. And people have been actually criticizing this pipeline for how hard is that to train, and also the stability and so on. Again, so basically this pipeline is that you have to first optimize the reward model over the preference data. Then you optimize the policy model according to the reward model. So that's basically like the leads to the motivation of all this like line of the offline of preference optimization. So why do we have to do this in like in 2 stages? Why not just directly learn the policy model from the preference data? Right? Why do we need to learn the reward model first and then optimize the policy model? So next, I'm going to talk about this very popular algorithm called direct preference optimization, or DPO, which was proposed by Stanford researchers last year in 2023. It has become really one of the most popular and the mainstream approaches for training the preference data. It has also become I think like the Llama stream models are basically only use the DPO, at least according to their report. Yeah.
Directly the pre-trained model. Can you use pre-trained model without any of this?
Without supervised fine-tuning? Oh.
Without RLHF, it go away.
Oh, I see. So if you just take the pre-trained model, these models actually not very. If you just chat with these models are not very good at like following the instructions, and there has been also a lot of safety concerns about these models. Yeah. And also, just by doing this post-training, these models have been basically shown to improve performance on basically all sorts of downstream tasks by a large margin. If we want to improve the like reasoning, improve the math, you actually have to do the post-training. It's just much better than just the pre-trained models. Yeah.
Like Misha's question, because in the last year there have also been works which propose to just do inference time re-ranking, right, where you don't really do any like the second part of like fine-tuning the model using preference data, but rather use the reward function to re-rank like a slightly larger list of outputs and then
I think right now this is still a really important debate. So right now a lot of people argue that how much like a compute budget you should put in inference time. If you put more budget, like more compute during inference time, you can always get a better performance. But if you put more like training on the post-training stage, and you can just do sampling or greedy search, then you can directly get a good performance. So there is always a trade-off in terms of how the deployment of such models. Yeah. Okay, so next I'm going to quickly talk about what is this DPO, the direct preference optimization. Again, the input is still just this prompt, winning response and losing response data. And we are going to directly train the policy model, the language model, directly from this preference data. So the derivation of DPO is basically, you start from like an objective that's very similar to basic PPO, basically in such format, like you're trying to maximize the reward minus like a basic KO penalty here. So to make sure that the policy model will not deviate too much from the reference model. And if you look at this form, and just under the so basically like for the PPO, you have to first optimize the reward model and then write the policy model and try to optimize the reward policy model according to the reward model. But you actually rewrite this form. So basically, under like a general reward function R5 here, you can write the optimal policy basically in this form. So Zx here is basically a partition function here. So basically, you can write the reward function as a sorry, you can actually write the optimal policy as a function of any reward function here. So that means that you can basically rewrite the reward as a function of the optimal policy. So if you want to, instead of doing this like a two-stage pipeline, you first optimize the reward, and then you optimize the policy model. Essentially, you can directly plug this reward function into basically the Bradley ranking, Terry ranking objective. And then finally, you can directly derive the DPO objective by inserting when you write the reward as a function of the optimal policy, you can directly write the policy into this like Bradley Terry ranking objective. You can directly finally derive this DPO objective. Sorry, I know I went too fast. If I have not seen this before, it might be a bit too fast here. So how many people have seen the DPO objective before? So any questions about this DPO objective? Yeah. So basically the idea is instead of first optimizing the reward, and then learn the policy model according to the reward, you can actually write the reward as a function of the optimal policy. And because the reward model is actually learned from the preference data, and if you write the reward as actually a function of the optimal policy, you can directly plug basically this expression into the ranking objective. You can directly learn basically the policy model from the preference data. That's the basic idea. Okay, so I'm just going to move on. Otherwise, I can spend a lot of time on explaining the DPO. So basically, so this basically one simplified view of thinking about the how to reduce the two-stage optimization into this one single stage. You can directly learn the policy model from the preference data, and this actually turns out to work really well.
Is there other explanation about of the DPO objective? Like, if you don't view it as a reward model, like, is there a more direct explanation?
I think the whole point of DPO is actually derived from the IO objective. So you want to basically eliminate the basic optimization of the reward. So you write the reward as a basic function of the policy model and directly optimize the reward as a policy model. But next, this is actually the exact point I want to talk about next. Yeah. Yeah. Sorry.
The beta hyperparameter.
Yeah, beta is the hyperparameter, basically like controls the penalty between the SFT model and the policy model. Yeah. Sorry. Oh, sorry. This is basically if you write the reward as a policy, there should be a constant term there. That's the partition function. But if you insert this reward function into this ranking objective, this basically cancel out. So you will just write this. You only this term will left out here, and then you can just put this term here and this term here. Yeah.
So what's the effect of like if you increase beta like as a tendency to infinity? What happens?
Increase the beta's infinity.
For like what is the traditional range that beta's kept in? So I'm just trying to understand the behavior.
So beta is basically controls. Beta is actually derived. So beta basically controls. I don't actually think that people set a very big value for beta. Beta basically controls this KO penalty.
Okay.
Yeah. So if beta is set to 0, basically you just don't control how far this kind of policy model will actually deviate.
Okay.
Yeah. Yeah.
Thank you.
Go ahead. Yeah.
Can you intuitively explain why the normalization or non-existent normalization, why divide by look at it relative to the reference and not because you're also going to add another term that, if I understand correctly, that says that you want to stay close to the reference.
Yeah.
So why does the reference distribution have to come in here intuitively?
Actually, that's exactly the thing I want to talk about next.
Okay.
But this actually is how the DPO objective is derived from. DPO objective is derived from this PPO objective, which has this KO term that actually claims to be very important to control how far the SFT model actually deviates from the reference model. The reference model is the SFT model. In the next few slides, I'm actually exactly going to talk about, I think the reference model is actually not necessary. Yeah. Okay, so if we just forget about all the math, like how DPO is actually derived from the PPO objective, essentially DPO is just one algorithm. It's one training objective that you can actually learn from the preference data, right? It's just like one object. It could be many. It's just a pairwise data. There are many objectives you can think about just to learn from the preference data. But DPO is one way that actually derived from the PPO, and I just want to list out a bunch of the other training objectives you can think about that you can actually use to learn from the preference data. So actually, there are actually a few works that actually even come out before DPO, but DPO has become really the mainstream and the most popular method here. So I list a bunch of different objectives here. So some of these use the hinge loss. So some of this still like DPO that derive from this like a Bradley ranking, Terry ranking objective. And there are also some other different objectives here. I also colored some of these objectives as yellow here. I just want to mention that these objectives do not actually have the reference term here. So it doesn't have this pi-ref in all of these objectives. But for the other objects like DPO, IPO, KTO, they actually have the pi-ref, the reference term here. So all of these objectives come from like different derivation or come from different like explanation motivations. But the DPO is just one of them that actually derived from this like PPO objective. Okay, so we actually have conducted lots of experiments trying to compare all these different objectives. So this also really depends on the experimental setting. But at least for this particular experimental setting that I'm actually going to explain, we actually don't find that, so different objectives could actually work very differently, but none of them actually outperform the DPO objective. So I'll tell you more numbers later about this kind of experimental setting. But in general, there are actually many ways you can think about how to design objectives for learning from the preference data. So next, I'm going to tell you one piece of work that we actually did in 2 or 3 months ago. So it's called SimPO. So this work was done by 2 students, Yu Meng and Meng Zhou here. So the title of this paper is called Simple Preference Monetization with a Reference-Free Reward. So we start with a very simple observation. Observation here is, so we know the DPO training. Essentially, we just try to learn this ranking objective. And this reward function is written as a beta times the log of the policy model divided by the reference model, right? And we are trying to basically maximize the reward, maximize the distance, the difference between the reward of the winning response and the losing response. But during inference time, essentially, we just take this the reward function. We essentially just take this policy model, and we start from the prompt X, and we are going to generate the response Y, right? So during the inference, essentially, we just do the greedy search or bin search, or like just do directly sampling. And we don't actually use any of the pi-ref, the reference model at all during the inference time. So what should be the role of the reference model at all here? Okay, so basically, if you ask me a question, why do we need the reference model? If during the inference time, essentially we try to maximize the difference between the 2 rewards. And during inference time, we essentially just try to maximize. This is a path, given the X, we are trying to generate the Y according to this policy model. Okay, so we actually did an analysis here. So we basically after we train a DPO model, and we evaluate basically the reward of the winning response and losing response, and also the probability of the winning response and losing response. We found they're actually not correlated at all. So that means that if we train model with DPO, essentially we don't find just basically evaluate on a held up set. So we find the winning response that is not necessarily assigned a higher probability than the losing than the probability of the losing response. So they're actually not well correlated. So this basically the number of examples on the held set. This basically the according to this reward function, basically the winning response or the reward of winning response is greater than the losing response, or smaller, or the greater the probability of the winning and the losing and the probability of the losing response. Okay.
Sorry, what is is the probability of winning and losing response is just the empirically?
Yeah, it's actually the average of log likelihood. So we basically found like if we train with DPO, and then we look at basically like what probabilities that actually assign this model assign to the winning and losing response on a held out set. We find that actually they are basically the reward and also the probability that we actually believe is more important during decoding actually not well correlated. So there's actually some concurrent work actually from Ken Cho's group and many other collaborators here. They also find that if you train with a DPO objective, it actually do not well properly learn the preference rankings. So there's a clear discrepancy between the reward function in the DPO and also the decoding metrics that we use to decode the policy model, basically the final language model. Okay, so just in response to this observation, so we propose a very simple objective. We call it SimPO objective. So we simply just get rid of the reference model. We simply use the average log likelihood as a reward function. So basically, we just simply define this reward function as this beta is a hyperparameter, still the hyperparameter of basically defined as the log likelihood of the y given x, and divided by the length of the y. And the y, so one question you might ask, why do we actually take this like a length normalization term? Why is this term actually length normalized? So I think this still requires a lot like a deeper analysis here. But in general, we believe that if you take the average of the log likelihood, this will be actually closer to actually the how we actually do the decoding in practice. So because the shorter sequences tend to have actually larger log likelihood. So if you do the basically the average turn, it will actually gives you like you actually will not stop at the shortened sequences. And these days we actually use large language models to like for example to do decoding to select the options for multiple choice questions. Actually, people always use the average of log likelihood instead of just log likelihood. So we actually find this length normalization term is actually very important for like this reward function. If you don't have this like average term, it actually doesn't work at all. Okay.
Sorry, could you repeat the intuition for why the average term does work, but without averaging?
Because if we just do the log likelihood, and but during the inference time, we actually do the greedy search. But if you just do all the bin serial sampling, so the average turn is definitely closer to actually what has been done in the inference time. It's not exactly the term that we used in inference, but it's actually better than just using log likelihood. Yeah.
Just like the summation is over the tokens of y in a causal way.
Yes. Yeah. Okay. Yes. Yeah. Okay. So second thing we actually added here. So we also added like a margin term in this Bradley Terry ranking objective gamma here. So here, this is more like an empirical choice. We actually in the Bradley Terry ranking objective, actually historically it could also include like a margin term. This is called like home advantage. But here we find that if we add like a margin term to encourage a larger margin between the winning and losing responses, this would actually work better in practice. So we have a lot of analysis in the paper to show the importance of this length normalization term and also the margin term. Okay, so let me just put things together. So compared to the DPO objective, here we get rid of the reference model. We simply just use the average of log likelihood as a reward function. And we plug this new simple reward function into the Bradley term ranking objective. We add like another margin term. And then finally, we can just derive this objective, a simple objective for learning from the preference data. So if you compare the DPO and the simple, so basically the difference here is that we don't have the reference. We don't have the reference model here, but we add the length normalization, and we also add a margin term here. So in the paper, we actually did a lot of analysis showing why we actually really need this length normalization. If you don't add this length normalization, essentially the model will basically encourage the model to only learn from the basically longer outputs, to encourage the model to learning from the longer outputs. That's usually actually really a problem in like learning, because a lot of models just try to generate longer outputs, and that's actually not what we actually want. Yeah. So yeah. Okay, the computational requirement is one extra thing, but that is actually not a big thing, because you can actually pre-compute those and cache those. But the main thing here is actually if you, okay, I'll just go back to this. The main thing here is if we add, so first we believe that the reference term is actually not used at all during the inference time. So during inference time, we essentially just do the greedy search or bin search or sampling. So we think there's a discrepancy between what the real model function is doing and what is actually done during the inference. Second, according to this observation, we find that the probability, if we just learn from this, like using this reference or reward function that according with this reference term, it actually doesn't assign a higher probability to the winning response compared to the losing response. So this basically shows that they're actually not well correlated.
Good role of stabilize the training, right?
So right now I'm telling you that there is a discrepancy between the training and the inference. That's basically the whole motivation.
Yeah, do you have like similar graph after using your SimPO for this figure?
Because the SimPO is just using this term, so it would be definitely like this. Yeah.
Yeah. So if you, in your preference data, if length was not correlated, then you still need that, like, does it still help to have the length normalization?
Yeah, if we don't have length normalization, the model will basically like really collapse. Actually, we'll only learn the basics the pairs from that longer output. The winning response actually longer than the winning. Yeah. I see. I think that could work. I don't know. Yeah.
I was wondering if that's just a
Oh, I see. Yeah. I agree. Yeah. Okay, so at this point, I can directly just show you basically a lot of results why I think that simple objective could work better than the DPO objective. But in the next few slides, I actually want to spend a bit more time taking a closer look at how we actually evaluate and compare these like different preference optimization methods. And I will then go back to show you what is the role of the data in the preference learning. So we actually have conducted like a pretty like a thorough experiment in this paper, but I want to tell you, sorry, I should have that part. Yeah. So basically, first we picked two model families. So the Llama, but both are not that big models, like an 8 billion model, Llama 3 model, and the Mistral 7 billion model. And we consider two settings. The first setting is the base model, and the second setting is the instruct model. The base model, basically, we just directly take the pre-trained checkpoints. And the instruct model, essentially, we take the instruct model that have been released by Mistral and Meta. So we actually don't really know what instruction tuning has been already done in the instruct models. We directly take this off-the-shelf instruction tuning models. So basically, the procedure and the training data are actually still opaque in this instruct setting. Okay, so the base setting here, essentially, so we actually followed another model called Zephyr from Hugging Face. So the base model, essentially, we try to just use the open source data set to do the supervised fine-tuning and the preference learning by ourselves. So we first fine-tune on the actual chat data for instruction tuning. And then we train on the actual feedback for preference optimization. So these are essentially two static data sets. One is for instruction tuning, one is for preference optimization. So just want to give you an idea about what actually has been done here in practice. So actual chat is actually a multi-turn conversational data. The prompt are initiated by humans, but the responses are actually generated by ChatGPT. So it's one of the bigger, and the diverse, high-quality instruction tuning data set out there called actual chat. And there is another data set, is a static preference learning data set called actual feedback. So it's actual feedback essentially takes the prompts from the many different sources, and then to generate the responses from the 4 different large language models, including Llama, including GPT-4, ChatGPT, and so on, including 4 different large language models. And then use GPT-4 to give a score. So basically, this is not a human preference. It's actually the feedback data that actually generated by GPT-4. So they use GPT-4 to score, like basically in 4 different dimensions, including instruction following, truthfulness, honesty, and helpfulness. And they pick basically the winning response as a response that actually received the highest average score in these 4 dimensions, and the losing response as a random of the remaining 3. Okay, so I just want to give you a sense about this are kind of how the current instruction tuning data sets and the preference learning data sets were generated. And this is basically the setting we use for like comparing the base setting. We start from the pre-trained model. We do the supervised fine-tuning by ourselves, and then we compare the different preference learning of methods on the actual feedback. And the second setting we call instruct setting. Here is actually more interesting. Here is we directly take an off-the-shelf instruction tuned model as a supervised fine-tuned model. And then we are going to generate the preference learning data by ourselves. So we essentially just take all the prompts from the actual feedback data set. We don't take their response, their ratings. We generate the 5 responses from each of the actual feedback prompts. And here we actually use the off-the-shelf reward model to pick the highest score, highest response as a winning response, and the lowest one as a losing response. I know these are very detailed things, but later I will tell you this will really make a difference. The 2 settings. One setting is that we start from the base model. We do the instruction tuning and the preference optimization using 2 static data sets. But here the instruction setting is we start from instruction tuned model, and then we are going to use basically the actual feedback prompts to generate the own policy data, basically generate the responses from the supervised fine-tuning model. And then we use an additional reward model to pick the highest one, highest score, and also the lowest score as the winning response and losing response. So the preference data here is actually generated by the SFT model. And there is also one actual reward model involved here. So in this case, it's actually even implemented by a bidirectional model called the Barton model. And finally, I want to talk about the evaluation we did here. So here we consider I think it's still pretty popular 3 evaluation setting: Alpaca Eval 2, Arena Hard, and Empty Bench. Alpaca Eval is from Stanford Taskix group. Arena Hard and Empty Bench is from here, LMC's here team. So basically, so all of this evaluation basically follow this protocol. So you have a set of prompts, and you have a baseline model. So here, the baseline model is basically GPT-4 model. And then you use your model to generate a response to these prompts. And so now you get 2 responses. And then you use a judge model. In this case, it's always GPT-4 Turbo to decide which is actually better. So basically, the final metric is basically like a win rate. What is the percentage of the examples that your response would actually rank over the baseline model, the one version of GPT-4 model? So that's basically the winning rate. And for the empty bench, it's just like a single scalar for the rating. I want to get a sense how many people have seen this such an evaluation before, like familiar with this. So it's basically like using large language model judge. So there could be a lot of discussion in that space too, like whether this is actually really a reliable evaluation or not. But this basically is the current like a standard practice of evaluating this kind of chat models. Okay, so next I'm going to show you the results. So as I said, there are actually some base setting and also the instruction setting. The instruct setting, essentially, we just start with an instruct model, and we are going to generate the own policy preference data by ourselves. And we are going to show like how this kind of preference learning can further improve the performance of the existing instruction-tuned models. So as you can see from this figure, the first thing you can see is SimPO is basically consistently and significantly better than DPO in all these settings. But we also find that if you have actually stronger instruct setting model, actually the improvements from like the preference learning methods would actually become smaller. So it's actually really more about the base model and also the preference data that you use to run the preference learning methods. But the second takeaway here is we find that you can actually build a quite strong chat model by just using open source data sets. So if we just start from like a base model and then you use a SimPO on the like open source model data sets like Ultra Feedback, you can get a 22% winning rate. But like the off-the-shelf Llama 3 8 billion instruct model has only like a winning rate of 26%. But the third thing I want to mention is, if you start with a very strong instruction-tuned model, and then you use this model to generate the preference data, you can actually further bring the performance by a lot. So for example, you can actually get the performance from 26 to actually like a winning rate of 44.7. Okay. Is there any question about this kind of experiment settings? Okay, so another thing I want to tell you is, you might, my guess is that like this kind of new instruct setting is actually something probably people are not familiar with. That really means that you can start with an instruct model. You can actually use the instruct model to generate own policy preference data. And then you can use the off-the-shelf reward model to decide like which is the winning response and which is the losing response. And this model can give you actually much stronger performance compared to the initial instruction-tuned model. And another result I want to show you here is, after we released the first version of the SimPO model, we actually produced another second version of the SimPO model. The only change here is that we actually basically change the reward model from the pair IM model I just mentioned to another stronger reward model. And then we find the performance could increase a lot from 44% winning rate to 53% winning rate. This is a winning rate compared to GPT-4 model. So this is actually a pretty big improvement. So think about the pipeline of the PPO again. So PPO is that you first learn a reward model, and then you are going to optimize the policy model according to the reward model. Now the situation here is you start with the you start from a pretty strong SFT model. You are going to generate the preference data, own policy preference data using the current model. And then you have an additional reward model to decide which is actually the winning response and which is the losing response. And then you get the final model using this offline preference optimization methods. So the key message here I actually want to send here is, because this kind of policy for training the preference optimization models. So I actually think the boundary between the online preference optimization and the offline preference optimization can be actually become actually more blurred. Basically, you still generate the own policy preference data and apply any of this kind of offline preference optimization and achieve very strong performance. And you actually can still train additional reward model. And this reward model can be even any other model, could be a bidirectional model, could be trained on many other resources. Okay, so this is basically one thing I want to tell you here. And I'm not going to tell you more about this, but we also tried out basically the SimPO on other base models. For example, we switched from the Llama 3 model to Gemma 2 model. We actually observed very strong performance, like the AlpacaEval, the winning rate is actually 72%. But what is actually really interesting to think about is actually what does this preference learning actually do? And how does this actually impact the general capacity of the model, such as math and reasoning? We find that if we do the preference learning optimization over, let's say, Gemma 2 model, we can still get a very strong performance on, like, say, MLU and the math data sets. But it actually has a very different results for the Llama model. And so what is actually really the difference between the base models that actually makes a difference in terms of the preference optimization? So this is still kind of an open question that we are actually not so sure at this point. Yeah. Okay, so I'll quickly wrap up this part. So I think up to this point, there has been actually still a lot of the discussion between PPO versus DPO, whether online or offline preference optimization, which one should actually work better. There is a very nice paper from our institute here that trying to unpack the different factors in comparing the DPO and the PPO. They find that actually the preference data quality actually is most important. And the second choice is actually the algorithm choice. So in all these papers, they still show that PPO has an advantage over the DPO. But I found that actually in all these experiments, they actually use the static preference data that is actually pre-generated. So like the ultra feedback. So you take collect a bunch of prompts, you generate like a lot of responses from the different large language models. But if you use your SST model to generate the preference data, so you use this prompt, this kind of on policy data, I actually find the gap between the online and the offline preference optimization will become actually much, much smaller. So that's kind of my current understanding of this space. Finally, I just want to mention this kind of actually what has been done in practice in the Llama 3, the post-training pipeline. You don't have to understand everything here, but the blue box here are actually the reward model, supervised fine-tuning model, and the DPO model. So the key features here is, first, they actually do multiple rounds of the data generation and model training. And they never use actually any static data. They always generate their own policy data instead of the static pre-generated data. So they always have a reward model. And the reward model will actually help you to generate the own policy preference data and also SFT data. And this data will be used to train the SFT model and the DPO model for the next round. And they iterate do this, and for multiple rounds. And finally, you achieve a very strong model. So what I want to emphasize here is really the own policy data that has been generated by all these models is actually very important. And you can just use the offline preference optimization instead of the online optimization. And finally, they also do like the model averaging of the models at different rounds, and they have found that the models can actually keep improving if you do this in multiple rounds. This is actually what has been done in practice. So actually the boundary between SFT and also the preference optimization has become really more and more blurred, because you have to use a reward model to help you generate SFT model, and also use data to generate the full training DPO model, and so on. You keep just repeating this training loop. Okay, so this is basically everything I have prepared for the post-training part. I just want to check when should do I need to stop? Like 3:40. Okay, yeah. I want to pause and see if people have any questions about this part, because I still have one part about the pre-training, but I can go really fast about that part. Yeah.
Do you think there will be like a maximum number of rounds you can go with this?
That I don't know. I think they did 6 rounds. Yeah.
When you compare like DPO with SFT, does the SFT model see the same data, the preference data that is used in DPO? Like what if you took the SFT model and you just kept fine tuning it on only the winning responses in the preference data?
Yeah, that's a good question. Honestly, I also feel like we haven't really like kind of reached the kind of the end of the SFT model at this point.
Yeah, because otherwise it's kind of an unfair comparison with that. So the SFT model doesn't see any of the preference data at all, right?
I don't get why it's not a fair comparison here. Yeah.
Not only is the objective different or the algorithm, but you're also changing the data.
Yes. Yeah.
It's hard to know if the difference is because of the algorithm or if it's just because of the difference in data.
I agree, but usually the preference optimization model start from the SFT and start from there. And also the preference data is always comes with this pair of the winning and losing response, right?
Yeah, I guess I'm saying you could just use the winning.
Yeah, I know. Yeah.
At least conceptually, is that winning minus losing gives you some direction that you can add to winning to do even better than the best response. So DPO is supposed to help you get better than the best response, but SFT will not. You kind of will always match the best response. So I don't know if it plays out in practice, but that's the hope, I guess.
So on that note, do you have any intuition about why do we need to plug in SFT in between doing this iteration on the DPO? I mean, empirically, it feels like this should work better, but I cannot pin down why I feel that way.
As at least in the experiment we showed earlier, like DPO needs to use the on-policy data generated by SFT model. If the starting point of that model is too weak, it cannot really even generate the responses that can be used to rank.
Right, but the first part I understand, but you said this is like iterating through multiple rounds. And I assumed that the previous round of DPO results might be strong enough to continue on just DPO iterations.
Maybe they just want to do
Or
they just personally
pipeline
so well that they don't want to change maybe. But sometimes it also.
But the SFT model is also the data is also come from a user reward model.
Yeah.
So, yeah.
I no, but I kind of feel like this might actually there may be a reason as to why this is a better thing to do. Mm-hmm. I mean, SFT is like so efficient in the way that it changes the policy to mimic the best experiences, which is also why learning in general works really well for distilling from larger models. But it's just like, we all believe that DPO is supposed to be correctly optimizing the best thing, and, reward is a better thing than look likelihood. And so something is clashing in my mind. But this doesn't feel like this might work better. I could believe that this is going to work better. I don't know why.
One thing that I don't know if this is the right answer, but like sometimes there are formattings that change when you go through rounds. And if you just did DPO where there is some change, like the models latch on fully to that, so they had to do something like they mask out certain tokens while applying the loss, like which would have otherwise been taking all the kind of updated a lot. So I wonder if SFT will also help avoid things like that, where it prevents some very spurious things to get over amplified.
So maybe building on that intuition, maybe what's happening is that the DPO, even though in the equation it looks all very nice, but the credit assignment is always super tricky. Whereas SFT does much better job at teaching the prefix all the way through the sequence.
Yes. I think DPO you can pick up many different
that works. Yeah, that works.
Okay, I would love to actually go back to trial experiment. I actually don't know. Yeah. Any other questions before I actually still talk a bit about the pre-training? Yeah.
Quick one.
Yeah.
So I wonder if, like, because you said in the reward mode boundary is quite vague.
Yeah.
So you also mentioned the alpha using win rate.
Yeah.
I wonder if people will directly use this alpha evaluation as a reward model to tweak this benchmark to verify. Just wondering if some people did that. Like you just directly use GPT for both.
Yeah.
So we have that number be super high. That's
So you're basically saying whether the reward model has been even trained on alpaca eval prompts.
no, I mean it's like a new way to tweak the test benchmark. You directly use GPT-4o as the reward mode, and then collect data point. So that's that way alpaca eval number will be super high. I just wonder if that will happen.
Okay, I will think about this and get back to you. Yeah. Yeah, I actually don't know if you actually did. Yeah. Okay, I'm actually glad that I switched the order of the pre-training and the post-training. So in the next under 20 minutes, I will just quickly go over the pre-training part, because I think there are actually a lot of details in the pre-training actually really vague to us. But I still think there will be actually lots of interesting research questions to think about. Yeah. Okay, so we all know what is a pre-training. So in a very simple words, we can just think about the pre-training as first we try to prepare like a high quality tokenized pre-training corpus, probably at the internet scale. Second, we decide a transformer model architecture and also context window size. Third, we are going to fit the model on the pre-training corpus to maximize log likelihood. So this pipeline has never been changed like since the GPT-1 model, right? So it's always like this objective. So all the only changes, like let's say for example in the latest Llama 3 model, is that really about the scale of the training corpus, the model architecture, and the context window size. So for the Llama 3 model, the largest model of the Llama 3 model, they pre-train a model with 400 billion parameters on 15.6 trillion tokens using a context size of 8,000 tokens. So this is the first stage. And this stage is followed by a continued pre-training stage that actually increase the context window to actually much longer, 128,000 tokens. So long context window language models is currently also a very important research topic. So what are some open research questions we can ask in the pre-training phase? So really, because the training paradigm has been really relatively fixed. So the most important question is really about the data. So how to curate and filter high quality pre-training data? And how should we decide a good data mixture? And what would be a good training recipe? So for example, how many stages of pre-training should we do to actually achieve a very strong model? And at every single stage of the pre-training, what kind of data mixture should we use? And there have been also a lot of really good studies for like starting scaling loss. So how should we decide the scaling loss for determining the model sizes and data mix? And then finally, also a very emergent research topic is how and when should we actually start to use synthetic data for pre-training. Just in the very limited time, I'm going to focus more on about actually the quality of the basic curation of the high quality pre-training data. So this is really the secret sauce of like basically all the industry like large language models, because all these companies they collect, curate like different like pre-training data, and they have to be very large, very diverse, and very high quality. And this actually really is the most important factor for deciding the performance of the pre-trained models. So as academic researchers or the researchers who don't have like enough resource, so what kind of things can we even study about pre-training corpus, right? So over the last few years, there has been actually a lot of really great community efforts trying to curate this kind of high quality pre-training corpus in the open. So I'll just give you some examples and something that people start looking at. So for example, this red pajama from Together AI more than 1 year ago, they try to curate this pre-training corpus that actually consists of like the different like a data mixture, including the common core and the C4. C4 is actually like the start from the T5 model. C4 is actually also a filtered version of the common core. And they also use like many other data mixtures, like from the many different sources, including like GitHub, books, archive, Wikipedia, and so on. And a couple of months ago, later, like the people start to actually do a lot of deduplication, try to clean this data. So the red pajama has 1.2 trillion tokens. And then Cerberus, this company, they actually produce this new corpus called Slim Pajama that has been actually, by just doing deduplication, they reduce the size of the pre-training corpus by a half. And another really important like pre-training corpus from Allen Institute is called this corpus called DOMA. So as you can see, that DOMA has a very different data composition, but still the largest subset is still common core, and followed by actually a lot of the high quality code data, and followed by C4. And they also throw in like a lot of like scientific research papers, and also like Wikipedia and books and so on. And I just want to mention, like, there's another trend for like curating pre-training data. It's actually just to use the internet data, the common core. So this data set called Refined Web actually is already also 1 year old. So the basis, actually, how many people know what is exact common core here? Just want to check. So common core is essentially just the crawled data from the like all the like web pages. Like a lot of snapshot of the web pages you can find. It's actually like a non-profit. I believe they basically collect a lot of like snapshot from time to time. So it's basically all about the web pages on the internet. So this is actually one trend that people start to just doing a lot of cleaning, and they believe that you can actually just start from the common core, and then you can actually try to curate a very high quality pre-training data from just the common core. So this refined web is actually a very exciting like development. They actually used to develop the Falcon model at the time, which considered 600 billion tokens. And actually even more recently, like Hugging Face released this data set called FineWeb, so which has 15 trillion tokens. So this is actually already comparable to the pre-training sites that actually using the Llama Stream model. And this is all about cleaning up the basically the common core like data set. Okay, so next I want to just tell you a bit about like kind of what kind of data processing pipeline have been actually used in this kind of pre-training data. So this actually is a data processing pipeline used in DOMA. So from the left to right, so they did like a language filtering because this is actually an English pre-training corpora. So they just keep only the English data set. And they did a lot of deduplication by URL. And they do the quality filters by heavily filter out the low quality data. And they try to remove like a lot of like toxic content and also the like a personal identifiable information that from the pre-trained corpus. And then finally, they do the deduplication based on the text tokens. So this is kind of like a one standard pipeline, but there have been actually a lot of many similar pipelines that have been used to actually really process the pre-training data. And the quality of the pre-training data is really decides a lot of the final performance of these models. What I want to emphasize here is actually the one step in this pipeline called quality filtering. So what kind of quality filters that people have been actually using to decide what what is actually really the high quality data in the pre-training corpus? So in this DOMA pipeline, so actually a lot of the quality filters actually come from this kind of like a lot of heuristics, like just a lot of rule-based filters. For example, they try to remove like any pages that fewer than 5 sentences, or they remove the lines that contain at least like less than 3 words. So these are actually very like a lot of heuristic-based things that happen here. One thing I want to emphasize here, you might feel surprised here, is this is actually really like a kind of new direction that people start to think about how to use the models to get model signals to actually train the quality filters to actually remove the kind of low quality data from the pre-trained corpus. And this could be actually really one of the most important directions for actually curating the high quality pre-training data. Next, I'm actually going to skip this part. So this year we actually did some work trying. So this project called curating. So we kind of try to leverage large language model signals for deciding what is actually the high quality signal in the pre-trained corpus. So I'm just going to skip this part. So the most important thing I really want to emphasize here is, so basically, like if we use like model-based training signals, we can actually this basically like trends that how can we actually generate like a lot of data for training the quality classifiers, and how can we get this kind of signals from? And we actually this year we did this work trying to define what is high quality data or quality signal in the pre-training data. Then we try to train a model called curator model from such like the signals, and then we use the models to actually decide, okay, these are the high quality data that we should use to pre-train language models. This should be the low quality data we should actually discard. And we also find that it's actually very important to balance between the quality and diversity. And this would really make a huge difference in terms of final performance of such models. And this has become actually really like a trend. So this is actually a very exciting development called FanWeb EDU. What they have done is basically like they try to use large language models to generate a lot of synthetic data. And they use this synthetic data to develop classifiers for identifying the educational content in the basically in the pre-trained corpus. And what they did here is basically you take a lot of the web pages, and they use the Llama 3 70 billion instruct model to decide whether this document contains educational value or not. And then they basically just train like a quality classifier based on this 450,000 annotations. And they found that this actually makes a huge difference. Like if we just use this kind of synthetic data to train a quality classifier and only train on the documents that contain the high educational values, and this would really change the basically the learning curves of the pre-training. So the y-axis here is basically like the downstream task performance on different NLP benchmarks, MMOU and ARC. So if you do this very aggressive like quality filters, it actually really makes a huge difference. Like so, these are like the other different like the types of pre-trained corpus, including like DOMA, C4, FanWeb, and so on. So this kind of direction, how to really train model-based filters to actually decide high-quality pre-training data, I think it's still at the beginning. And people in the next year or few years, people will do a lot of such attempts to really figure out what should be the high-quality data used in the pre-training data. And to give you a sense about how this kind of synthetic data has been really generated. So they basically take like a web page document from the FanWeb and they write like such a long prompt. The prompt is basically like below is the extract from the web page. Evaluate whether the page has an educational value and could be useful in an educational setting, blah, blah, and then at one point, if it satisfies something, and then basically write a very long prompt and ask the Llama 3 instruct model to give you this kind of score for rating the educational value. And finally, you can you also ask the model to even justify why this actually should give you such a high score. Yeah. And this kind of some ongoing work we are doing right now. So we are actually really trying to understand basically like what these kind of quality filters can give us and why these kind of quality signals can actually really make the performance of the large language model so different. So we actually try to understand like according to different topics and formats. So it really can give us a very like an intuitive understanding of what these quality filters have been doing. And then finally, I just want to give a shout out to like this really big team efforts like done by a lot of researchers here called data comp language model competition. Basically, the idea here is let's just try to fix the language model. And I'll give you like a kind of like a very large unfiltered pre-training corpus. So what can you do to filter the data? So everything here is basically about how to filter the common crowd data. And you can also mix high quality data such as Wikipedia books, and that is basically your choice. And you should figure out how to filter the pre-training data from like a large set of unfiltered covers. And then you fix the model training, you fix the evaluation, and really to figure out what is really the deciding factors in like basically impacting the performance of the pre-trained models. And they actually also produce a very strong baseline for this competition, and they basically found the model-based filters will be actually really the key to assembling a high-quality training set. Okay, so I'm not going to talk too much here. There's also a lot of heuristics here. It's actually about the domain mixture and also the multiple stage training. So actually there are a lot of secret sources in all these kind of different large language models. Basically, in pre-training these models, people have to do like a different stages. And at the different stages, you have to decide basically the data mixture like of the different domains. And this has been really decided by heuristic or some human experiences. Honestly, I don't know how they exactly decide this domain mixture. But it's actually really the key secret and the key secret source to for deciding the performance of these models. And another thing I want to mention is just people have started to actually put in the supervised fine-tuning data in the pre-training as well. And this has been also basically makes a boundary between the pre-training and also supervised fine-tuning become more blurred. And there has been actually a lot of things you can think about to actually for adjusting the domain mixture that I'm not going to talk about here. And finally, there has been also some studies trying to study the scaling laws of for deciding the domain mixture. Even for the Llama 3 paper, they figure out like several steps for deciding what should be a good data mixture. So they first perform like some experiments on like a bunch of the small models and to predict the performance of the large language models on this domain mixture. And they have to repeat this process and then figure out what should be the new data mixture for like the training the next round of the models. And there has been really a nice paper for this, like trying to figure out this kind of scaling laws for predicting the different data mixtures. Finally, I'm just going to tell you, like, basically people have been seeing a lot about the different research topics in pre-training, but it has been really hard to do just given the scale of all these experiments. So one thing actually my group is actually also thinking about a lot is actually long context pre-training. So long context pre-training, usually you have to do also 2 stages. First, you have to do the short context pre-training, and then you have to switch to long context at one point. Now, how can you even mix the short context data and long context data, and how can you recover the performance of the short context task? And there have been also a lot of attempts for actually rephrasing the pre-training data or directly using the synthetic data in pre-training. And finally, I definitely didn't plan to talk about is actually the model architectures beyond transformers and also the training objectives beyond the next token predictions. So I have been a lot of things that people are actively working on, and feel free to check out these references if you're interested. Okay, so basically, I basically plan to just wrap up here. And thanks.
We have to take questions offline. Danqi is around till tomorrow evening, so you can find enough time to chat with her. We'll have to come back for Jacob's talk in like 10 minutes. We'll start at 2:55. You can take the questions outside. Sorry about that. Please hang Danqi again.